Look up on any clear night, and you're gazing into an ocean of mysteries. Between the familiar constellations and the steady march of planets across the dome of darkness, there exist phenomena so strange, so utterly baffling, that even our most brilliant minds struggle to explain them. These aren't the predictable rhythms of celestial mechanics, or the well-understood fusion reactions of distant suns. No, these are the cosmic enigmas that keep astronomers awake at night, the observations that refuse to fit neatly into our current understanding of physics, the signals and objects that whisper of processes we've yet to comprehend. Tonight, we're going to explore some of the most perplexing mysteries that the universe has placed in our sky. From radio signals that flash for mere milliseconds, yet release more energy than our sun produces in days, to interstellar visitors that behave in ways we never predicted, to the very fabric of space-time itself harbouring secrets that challenge the foundations of physics. These mysteries aren't just curiosities, they're windows into the unknown, clues to understanding the deeper workings of reality itself. What makes these objects truly mesmerising is not just their strangeness, but the stories behind their discovery. The careful observations, the sudden realizations, the debates and controversies that follow. Science doesn't advance through certainty alone. It advances through mystery, through the courage to admit when we simply don't know, and through the relentless human drive to understand what we're seeing in the darkness above. So settle in. Dim the lights if you can. Let's explore together the most mysterious objects in our sky, and perhaps along the way, we'll glimpse something of the profound strangeness of the cosmos we call home. If you enjoy calm, immersive journeys through the universe, consider subscribing so you don't miss the next one. Now, get comfortable, and let the story begin. On August 15th, 2007, astronomer Duncan Lorimer and his student David Narkovich were doing something that might sound tedious to most people, but is actually the bread and butter of astronomy. They were combing through archival data from pulsar surveys, looking at old observations with fresh eyes. And then they found it, a signal so brief, so powerful, so utterly unexpected, that it would launch an entirely new field of astronomical research. The signal lasted less than 5 milliseconds, but in that fleeting instant, it released as much energy as the sun produces in 3 entire days. When they calculated where it came from, they realized it hadn't originated in our galaxy at all. This burst of radio waves had traveled across billions of light-years of space to reach Earth. They called it the Lorimer burst, and it was the first fast radio burst ever detected. At first, there was skepticism. Could it have been some kind of interference? A glitch in the equipment? Radio telescopes are sensitive instruments, and they pick up all sorts of terrestrial noise. Cell phone towers, satellites, even microwave ovens can create signals that might confuse an analysis. But as Lorimer and his colleagues investigated further, the evidence became overwhelming. This signal bore all the hallmarks of having travelled through intergalactic space. The way its different frequencies arrived at slightly different times, a phenomenon called dispersion, told a story of a signal that had passed through vast clouds of free electrons between galaxies. And then, in the years that followed, more were found. Dozens, then hundreds, then thousands of these fast radio bursts. The Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, has been particularly successful at detecting them. This radio telescope in British Columbia consists of 4 huge stationary receivers shaped like half pipes, tuned specifically to the frequencies where fast radio bursts are most common. Since it began operations in 2020, CHIME has detected thousands of these mysterious flashes. What makes fast radio bursts so fascinating is their sheer variety. Most of them are one-time events. They flash once and are never heard from again. We point our telescopes back at the same patch of sky, and there's nothing, just silence. But then there are the repeaters. Some sources flash over and over again, sometimes following patterns we can predict, other times behaving completely erratically. Take FRB 1809 Westin, for instance. This particular source seems to follow a schedule. It pulses for about 4 days, then goes dormant for about 12 days, creating a total cycle of roughly 16 1/3 days. It's the only fast radio burst we've found that repeats in such a regular pattern. What could cause such precise periodicity? Perhaps it's related to the rotation of whatever object is producing it, or maybe it involves two objects orbiting each other, with the geometry of their dance determining when we can see the bursts. The energy involved in these events is staggering. When we detect a fast radio burst, the signal that reaches Earth has been travelling for millions or even billions of years, weakening with every light year it crosses. Yet even after all that dilution, even after spreading out across the vast emptiness of space, the signal we detect is still measurably strong. Astronomers have calculated that by the time it reaches us, a typical fast radio burst is about 1,000 times weaker than the signal from a mobile phone on the moon. Think about that for a moment. That's already incredibly faint, and yet that's the attenuated version of an event that, at its source, was releasing more energy than our entire sun produces in days. For years, the origin of fast radio bursts remained one of astronomy's most perplexing mysteries. Theories proliferated. Could they be caused by neutron stars, black holes, merging stellar remnants? Some even wondered, half seriously, if they could be signals from extraterrestrial intelligence. After all, no natural process we knew of seemed capable of producing such intense, brief bursts of radio energy. Then came a breakthrough. On April 28, 2020, a fast radio burst was detected from within our own galaxy. It came from the direction of a known magnetar, a type of neutron star with an extraordinarily powerful magnetic field. SGR 1935 plus 2154, as this magnetar is designated, had been acting up, producing X-ray flares. And then it produced a radio burst that, had it occurred in a distant galaxy, would have looked exactly like the fast radio bursts astronomers had been detecting from across the cosmos. This was huge. It established beyond reasonable doubt that magnetars are at least one source of fast radio bursts. A magnetar is already an extreme object. It's a neutron star, meaning it's the collapsed core of a dead star, typically with about 1.4 times the mass of our Sun compressed into a sphere only about 20 kilometers across. The matter is so dense that a teaspoon of it would weigh about 1 billion tons on Earth. But a magnetar takes this extremity further. Its magnetic field is about 1 trillion times stronger than Earth's, strong enough to literally distort the vacuum of space around it. The exact mechanism that produces these bursts is still debated. One possibility involves starquakes. As a magnetar cools and its crust adjusts, it might crack, releasing enormous amounts of energy in the process. Another theory involves the magnetic field itself. Magnetar fields are so powerful they're unstable. Field lines can twist and tangle, building up stress, and then suddenly snap and reconnect in a process similar to what causes solar flares on our Sun, but vastly more powerful. But here's where it gets interesting. While magnetars can explain some fast radio bursts, they can't explain all of them. The CHIME telescope has catalogued thousands of these events now, and they come from all sorts of different environments. Some originate in galaxies that are actively forming stars, exactly where you'd expect to find young magnetars. But others come from old, dead galaxies, where star formation ceased billions of years ago. In February 2024, one fast radio burst was traced to the outskirts of an ancient elliptical galaxy, a place where magnetars shouldn't exist. This discovery was particularly surprising because it was so far from the galaxy's centre. If you imagine a galaxy as a city, with most of the action happening downtown, this fast radio burst was like finding a massive power plant in the middle of a desert, far from any infrastructure. Some researchers have speculated that it might have originated in a globular cluster, a dense ball of old stars orbiting in the galaxy's halo. But even that doesn't fully explain it. Globular clusters aren't supposed to harbour the kind of energetic processes that could produce fast radio bursts. Then there's the question of why some fast radio bursts repeat while others don't. Do they come from different types of sources? Or is it the same phenomenon but observed under different conditions? Recent research suggests there might indeed be two populations. The repeating bursts seem to come more often from regions with strong magnetic fields and lots of dense material, while the one-off bursts come from cleaner environments. This could suggest that the surrounding material affects whether we see repeated bursts or not. And here's another strange detail. Some fast radio bursts show a peculiar pattern in their radio frequencies. As researchers at the Allen Telescope Array observed FRB 22U2 NONOS 2A, they noticed that the center frequency of its burst was gradually decreasing over time. When they turned this into sound, mapping the frequencies to xylophone notes, it sounded like someone sliding down the keys, playing the lowest notes over and over toward the end. They called it a cosmic slide whistle. What could cause such a frequency drift? It might be related to changes in the source itself, or perhaps to something in the environment through which the burst is travelling. In 2025, astronomers detected what they informally called RBF Lote, the radio brightest flash of all time. This fast radio burst, originating from a galaxy about 130 million light-years away in the constellation Ursa Major, was so bright it initially caused confusion. Was it actually a fast radio burst or just some terrestrial interference? But the CHIME outrigger telescopes working together to create a network of observations confirmed its cosmic origin. The burst came from the edge of a star-forming region in the galaxy NGC 4141, providing valuable data about the environment where these events occur. Recent studies have also shown that fast radio bursts can tell us about more than just their sources. As these radio waves travel across the universe, they pass through all the matter between their source and Earth. This includes the diffuse clouds of gas and plasma that fill the space between galaxies. By studying how fast radio bursts are dispersed and polarized, astronomers can actually map out this intergalactic medium, solving another cosmic mystery in the process. For decades, cosmologists had predicted that there should be more ordinary matter in the universe than we could actually see. Fast radio bursts have helped confirm that much of this missing matter does indeed exist in these hard-to-detect intergalactic clouds. But despite all this progress, fast radio bursts still hold many secrets. We still don't know exactly what causes the most extreme ones. We don't know why some sources can produce thousands of bursts while others only flash once. We don't understand the relationship between the burst properties and the environment they occur in. Every answer seems to raise new questions. The story of fast radio bursts is still being written. As better telescopes come online, as we detect more of these events and study them in greater detail, we're slowly piecing together the puzzle. But for now, these cosmic radio flares remain one of the most active frontiers in astronomy, a reminder that the universe is filled with phenomena we're only beginning to understand. Every time a fast radio burst flashes across our detectors, travelling billions of years to reach us, it carries with it information about the most extreme physics in the cosmos, encrypted in patterns we're still learning to decode. On the night of October 19th, 2017, a telescope on the Hawaiian island of Maui detected something unprecedented. The Pan-Starsky telescope, which routinely scans the sky for asteroids and comets that might pose a threat to Earth, captured an object moving through our solar system. But this wasn't just any asteroid. When astronomers calculated its trajectory, they realized something extraordinary. This object was moving too fast, far too fast to be bound by the sun's gravity. It wasn't orbiting our star. It was just passing through, a visitor from interstellar space. They named it Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. And indeed, it was the first confirmed interstellar object ever detected passing through our solar system. But Oumuamua would prove to be far more than just a milestone. It would become one of the most debated objects in modern astronomy, exhibiting behaviours so strange that explanations range from exotic ices to, yes, even suggestions of alien technology. When Oumuamua was discovered, it had already rounded the Sun and was heading back out toward interstellar space. Astronomers had only a brief window to study it before it faded from view. What they saw in those few weeks was puzzling. The object's brightness varied dramatically as it tumbled through space, suggesting it had an extremely elongated shape. Initial calculations indicated it might be about 10 times as long as it was wide, like a cosmic cigar. Later refinement suggested it might be more disc-shaped, like a pancake, but either way its proportions were unlike anything seen in our solar system. And then there was the colour. Oumuamua had a distinctive reddish hue, similar to objects in the outer reaches of our solar system that have been bombarded by cosmic rays for millions of years. This suggested the object was old, very old, and had been wandering through the galaxy for an immense span of time before its chance encounter with our Sun. But the real mystery began when astronomers noticed something odd about Oumuamua's trajectory. As it flew away from the Sun, it was accelerating slightly more than gravity alone could explain. This is actually common behaviour for comets. As they warm up near the Sun, their ices vaporise, jetting out gas that gives the comet a tiny push, like a spacecraft firing thrusters. This outgassing also creates the characteristic tail that makes comets so visually spectacular. The problem was that Oumuamua didn't have a tail. Observations by the Hubble Space Telescope and others detected no coma, no cloud of gas and dust, no jets of material streaming away. Yet something was pushing it, giving it that extra acceleration. What could explain a comet-like push without any visible comet-like activity? The mystery deepened when astronomers realised how small Oumuamua was. Estimates suggested it was only about 100 to 400 metres long, much smaller than typical comets. This small size would actually make the outgassing problem worse. A small object has less surface area relative to its mass, so any gas it does produce should have a stronger effect on its motion. Yet the amount of acceleration observed was relatively modest, requiring only a tiny amount of mass to be ejected. Where was this mass coming from if not from visible outgassing? The scientific community began proposing explanations, each stranger than the last. One early hypothesis suggested that Oumuamua might be made of frozen nitrogen, like Pluto's surface. As it approached the Sun, this nitrogen could sublimate, turning directly from solid to gas. Nitrogen ice would be much shinier than typical comet material, which could explain why Oumuamua reflected so much sunlight. And nitrogen, being lighter than water or carbon dioxide, could provide thrust without carrying much dust with it, explaining the lack of a visible tail. But there were problems with this idea too. Nitrogen ice is fragile. Could an object made primarily of it really survive the journey through interstellar space? Researchers calculated that cosmic rays and collisions with dust grains would gradually erode such an object. They estimated that Oumuamua could only have survived about 500 million years in interstellar space if it were made of nitrogen ice. That's actually quite young on cosmic timescales, but it also means that if this hypothesis is correct, there must be many objects like Oumuamua being ejected from planetary systems throughout the galaxy to maintain the population we'd expect to encounter. Another idea proposed that Oumuamua could be made of ordinary water ice but with a twist. As it travelled through interstellar space for millions of years, high-energy cosmic rays would have bombarded its surface, breaking apart some of the water molecules. This process could trap hydrogen gas within the ice. Then, as Oumuamua warmed up near our Sun, this trapped hydrogen could be released. Hydrogen is the lightest element, so even a small amount of it escaping could provide the observed acceleration. And because hydrogen molecules are so light and small, they wouldn't carry much dust with them, explaining the lack of a visible tail. This hydrogen hypothesis has gained considerable support because it's elegant. It doesn't require Oumuamua to be made of exotic materials. It just requires it to be an ordinary water-rich comet that spent a long time in interstellar space. The cosmic ray bombardment it would experience during that journey is well understood. The physics of how hydrogen could be trapped in amorphous ice and then released when heated is straightforward. The hypothesis explains multiple aspects of Oumuamua's strange behaviour with a single, relatively simple mechanism. Yet even this explanation has its skeptics. Some researchers point out that Oumuamua's shape remains unexplained. Why would a comet be so elongated? Even accounting for erosion during its interstellar journey, the proportions seem extreme, and there's the matter of its trajectory. Oumuamua entered our solar system from the approximate direction of the star Vega, but Vega wasn't in that position 300,000 years ago, when Oumuamua would have passed through that region of space. So where did it actually come from? We may never know. And then, of course, there were the more speculative ideas. In December 2017, Avi Loeb, a respected astronomer at Harvard University, suggested that scientists should at least consider the possibility that Oumuamua could be artificial. He wasn't claiming it definitely was an alien spacecraft, but he argued that given its unusual properties, particularly its acceleration without visible outgassing and its extreme shape, the hypothesis shouldn't be dismissed out of hand. This suggestion ignited fierce debate. Most scientists argued that there was no need to invoke extraordinary explanations when natural ones would suffice. But Loeb countered that science should follow the evidence wherever it leads, and if an object exhibits properties we'd expect from a piece of technology, we should at least investigate that possibility. The attention Oumuamua received led to searches for other interstellar visitors. In 2019, a second interstellar object was discovered. Named 2I Borisov, it turned out to be decidedly less mysterious. It looked and behaved exactly like a comet from our own solar system, complete with a bright coma and tail. It had come from interstellar space, yes, but it didn't challenge our understanding of what comets should be. In a way, Borisov's normalcy made Oumuamua even more intriguing. If interstellar comets can be ordinary, why was our first detected visitor so strange? Astronomers estimate that there could be thousands of Oumuamua-sized interstellar objects within Neptune's orbit at any given time. We just can't see most of them because they're too small and too far away. Our telescope stumbled upon Oumuamua by chance, and only because its trajectory brought it close enough to Earth. As telescope technology improves, we'll likely discover many more interstellar visitors. Each one will help us understand the diversity of objects that wander the galaxy. The European Space Agency had plans for a mission called Comet Interceptor, designed to wait in space beyond the Moon's orbit, ready to quickly intercept and study the next interstellar object that passes through. This kind of rapid response mission would give us far more data than we could gather from Earth-based telescopes alone. Instead of a few weeks of hurried observations, a spacecraft could travel alongside an interstellar visitor, examining it in detail, measuring its composition, mapping its surface, understanding its structure. For now, Oumuamua is gone. It passed the orbit of Neptune in 2019 and is now beyond the reach of even our most powerful telescopes, fading into the interstellar darkness from which it came. It's heading roughly toward the constellation Pegasus, where it will wander for perhaps millions of years before its next encounter with another star system. Somewhere out there, in some unimaginably distant future, Oumuamua might pass through an alien solar system, and perhaps beings there will spot it with their own telescopes and wonder, as we did, about this strange traveller from afar. What Oumuamua taught us is that interstellar space isn't empty. Objects travel between the stars, carrying with them clues about the planetary systems that birthed them. Some of these objects are probably ordinary, like Borisov. Others might be as unusual as Oumuamua. Each one is a sample from a distant solar system, delivered to our doorstep by the vagaries of orbital mechanics, and each one challenges us to expand our understanding of what's possible. The debate about Oumuamua's nature continues. New papers are still being published, analysing the data from those precious few weeks when we could observe it. Some researchers favour the hydrogen hypothesis, others still think nitrogen ice is the answer, still others propose entirely different mechanisms. But all agree on one thing: we need to be ready when the next interstellar visitor arrives. Because the next Oumuamua might be even stranger, and this time we'll know to look for it. On the night of August 15th, 1977, while most of America slept, a radio telescope in Ohio was listening to the stars. The Big Ear telescope, operated by Ohio State University, was part of an ambitious project called SETI, the Search for Extraterrestrial Intelligence. Night after night it scanned the heavens, recording any radio signals it detected, searching for patterns that might indicate an artificial origin. For years it had found nothing but natural radio noise, and then at 11:16 p.m. Eastern Time, it detected something that would become one of the most famous events in the history of SETI. The signal lasted 72 seconds. That was how long the Big Ear's beam could observe any particular point in the sky, as Earth's rotation carried it past. During those 72 seconds, the signal was incredibly strong and remarkably narrow in frequency, centered almost exactly on 1420 MHz. This frequency is significant. It's the natural emission frequency of neutral hydrogen, the most abundant element in the universe. It's also in a part of the radio spectrum that's protected for astronomical research, where terrestrial transmissions are forbidden precisely because astronomers want to listen for signals at this frequency. A few days later, astronomer Jerry Ehman was reviewing the data printouts from that night. He noticed the sequence of characters 6EQUJ5, representing the signal's intensity as it rose and fell. The pattern was exactly what you'd expect from a signal passing through the telescope's beam. It started weak, grew stronger as the beam centered on the source, then faded away as Earth's rotation carried the beam past. Ehman was so struck by what he saw that he circled the sequence in red pen and wrote a single word in the margin: "Wow!" That annotation gave the signal its enduring name, the WOW. Signal has fascinated and puzzled researchers ever since. What made it so compelling was not just its strength or its frequency, but the way it matched, in almost every detail, what SETI researchers had predicted an extraterrestrial signal might look like. It was strong, narrow band, and occurred at a frequency that made sense for interstellar communication. If you were designing a beacon to be noticed across interstellar distances, you might choose exactly these characteristics. But there was a problem. The signal never repeated. Ehman and his colleagues immediately began searching for it again. They pointed the Big Ear back at the same patch of sky, night after night, but heard nothing. Other radio telescopes joined the search. The Very Large Array in New Mexico, with its far greater sensitivity, scanned the region. Nothing. The Greenbank Telescope in West Virginia, one of the largest radio telescopes in the world, listened. Still nothing. Decades passed, and despite numerous searches using increasingly sophisticated equipment, the WOW signal was never detected again. This lack of repetition was troubling. If the signal was from an extraterrestrial civilization, why would it appear only once? Perhaps it was a beacon that swept across the sky like a lighthouse, and we just happened to be in its beam for those 72 seconds. But then we should have seen it again when the beam came back around. Maybe it was a one-time broadcast, a message sent into space and then never repeated. But that seemed wasteful. Why go to the trouble of creating such a powerful signal if you're only going to transmit it once? Skeptics proposed various natural explanations. Perhaps it was interference from a satellite. But satellites move, and their signals would show a different pattern than what was observed. Perhaps it was reflection from space debris. But what kind of debris could reflect a signal so precisely, creating the exact pattern expected from a distant point source? Perhaps it was some kind of intermittent astronomical phenomenon we don't understand. But what natural process could create such a narrow band signal at exactly that frequency? In 2017, astronomer Antonio Paris proposed an intriguing hypothesis. He noted that two comets, 266P Christensen and 335P Gibbs, had been in roughly the same region of sky in 1977. Comets, he argued, are surrounded by clouds of hydrogen. Gas and this hydrogen could emit radiation at 1420 MHz. Perhaps the WOW signal was simply radio emission from a comet's hydrogen cloud. This explanation was quickly challenged. Other astronomers, including members of the original Big Ear team, pointed out several problems. First, the comets weren't actually in the telescope's beam at the right time. Second, comets don't emit strongly at this frequency. The hydrogen around comets is generally in the wrong state to produce such intense narrowband emission. And third, the Big Ear had 2 feed horns that should have detected the signal 3 minutes apart if it were from a stable source. The signal appeared in only 1 feed horn, suggesting it was either extremely brief or came from a very specific direction that one horn could see but the other couldn't. But then, in 2024, researchers presented a new hypothesis that has gained considerable attention. Using data from the Arecibo radio telescope in Puerto Rico, which unfortunately collapsed in 2020, they reported finding several signals that were somewhat similar to the WOW signal, though much weaker. These signals, they suggested, could be explained by a rare astrophysical phenomenon. Imagine a cold cloud of hydrogen in interstellar space. Now imagine a powerful source of radiation, perhaps a flare from a magnetar or some other energetic object, hitting this cloud. The radiation could excite the hydrogen, causing it to suddenly brighten in radio waves at exactly 1420 MHz, creating a brief, intense signal. This mechanism could explain several features of the WOW signal. It would be a transient event, appearing once and never repeating, because it requires a specific alignment between the hydrogen cloud, the radiation source, and Earth. It would be narrow band because it's coming from hydrogen. And it could be very bright because the cloud is essentially acting as a natural amplifier, a process known as a maser, similar to a laser but for radio waves instead of light. The key insight is that magnetars, the likely culprits for providing the energizing radiation, weren't even discovered until 1992, 15 years after the WOW signal. So in 1977, astronomers couldn't have proposed this explanation because they didn't know such objects existed. It's a reminder that sometimes explaining anomalous observations requires knowledge we haven't yet acquired. Yet even this explanation isn't universally accepted. Some researchers point out that the required alignment would be extremely rare, perhaps too rare to explain even one detection. Others note that we still don't fully understand all the details of how such a phenomenon would work. The debate continues, with new papers and analyses appearing regularly. What makes the WOW signal enduringly fascinating isn't just the mystery of its origin, but what it represents. For that brief moment in 1977, we detected something that looked exactly like what we were searching for. Whether it was a message from another civilization or a natural phenomenon we've yet to fully explain, it showed us that the universe is capable of producing signals that can genuinely surprise us. It reminded us that when we listen to the cosmos, we must be prepared for the unexpected. The search for extraterrestrial intelligence continues, now with more sophisticated instruments than ever. Projects like Breakthrough Listen use cutting-edge radio telescopes to scan the sky, looking for signals that might indicate technological civilizations. They've developed algorithms to sift through enormous amounts of data, searching for patterns that stand out from the natural radio noise of space. But so far, nothing like the WOW. Signal has been found. Some SETI researchers have broadened their search beyond just radio signals. They're looking for optical pulses, brief flashes of laser light that an advanced civilization might use for communication. They're searching for megastructures, enormous constructions that might block a star's light in detectable ways. They're looking for chemical signatures in exoplanet atmospheres that might indicate industrial activity. The search has become more diverse, more creative, as we realise that we don't know exactly what form an extraterrestrial technosignature might take. The Big Ear telescope itself is no longer operational. The land it occupied was sold in 1997, and the telescope was demolished to make way for a golf course. It's a somewhat ignominious end for an instrument that made one of the most intriguing detections in the history of astronomy. But its legacy lives on. The WOW signal remains a touchstone, a reminder that even a single unrepeated event can capture our imagination and fuel decades of investigation. In a way, the WOW signal represents everything that's challenging and exciting about SETI. The search is, by its nature, looking for something that might be extremely rare. We might scan 1,000,000 stars and find nothing, but the moment we do find something, if we ever do, it will be one of the most profound discoveries in human history. It will fundamentally change our understanding of our place in the cosmos. For now, the WOW signal remains unresolved. Was it a message from the stars, briefly glimpsed and then lost? Or was it a cosmic coincidence, a natural phenomenon that happened to mimic what we were looking for? We may never know for certain, but the fact that we're still investigating it nearly 50 years later speaks to the enduring human need to understand what we're seeing in the darkness above. And perhaps someday we'll detect another signal like it, and this time we'll be ready. Black holes have always occupied a special place in our imagination. These regions of space-time where gravity becomes so intense that not even light can escape have been the subject of countless stories, theories, and debates. For decades, they were thought to be simple objects, describable with just 3 numbers: their mass, their spin, and their electric charge. The physicist John Wheeler famously quipped that black holes have no hair, meaning they have no other distinguishing features. Everything that falls into a black hole, all the complexity and information about the matter that created it, seem to simply vanish. But in the 1970s, Stephen Hawking made a discovery that would complicate this picture dramatically. Working with quantum mechanics, the physics of the very small, Hawking realized something that seemed impossible. Black holes, he calculated, should emit radiation. They should glow, albeit extremely faintly, with a type of thermal radiation that would later bear his name. Hawking radiation represented a profound connection between quantum mechanics, thermodynamics, and general relativity. The mechanism behind Hawking radiation involves quantum fluctuations right at the edge of the black hole's event horizon, the point of no return beyond which nothing can escape. Quantum mechanics tells us that empty space isn't truly empty. Instead, it's filled with virtual particle pairs that constantly pop into existence and immediately annihilate each other. But near a black hole's event horizon, something strange can happen. One particle of a pair might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole has emitted a particle. Over immense spans of time, this process would cause the black hole to lose mass. Slowly, gradually, it would evaporate, eventually disappearing entirely. For a black hole the mass of our Sun, this evaporation would take about 10 to the power of 67 years, vastly longer than the current age of the universe. But for smaller black holes the process would be faster, and as the black hole shrinks, the radiation becomes more intense, leading to a final burst of energy as it disappears. This was already shocking enough. The idea that black holes, the ultimate prisons of the cosmos, could actually emit something challenged our understanding of what black holes were. But Hawking's calculation led to an even deeper problem, one that would occupy theoretical physicists for decades. The problem was information. In quantum mechanics, information is fundamental. The laws of quantum mechanics are reversible. In principle, if you know the final state of a system, you should be able to work backward and determine its initial state. Information cannot be destroyed. This principle, called unitarity, is central to how quantum mechanics works. But Hawking's calculation seemed to violate this principle. As matter falls into a black hole, it carries with it information. Information about what kind of matter it was, its quantum state, its properties. But according to Hawking's calculation, the radiation that comes out is purely thermal. It's random, carrying no information about what went into the black hole. It's like the difference between burning a book and analysing the smoke and ash. The thermal properties of the smoke tell you a fire occurred, but they don't tell you what was written in the book. So what happens to the information when the black hole finally evaporates completely? Does it just vanish? That would violate quantum mechanics. But if it doesn't vanish, where does it go? The radiation seems to be information-free. This became known as the black hole information paradox, and it stumped physicists for decades. Some physicists, including Hawking himself for many years, were willing to accept that maybe quantum mechanics needed to be modified. Maybe, in these extreme conditions, information could be destroyed after all. But most physicists were deeply uncomfortable with this idea. Quantum mechanics is one of the most successful theories in physics. Every experimental test has confirmed its predictions. To modify it in such a fundamental way would require compelling evidence. Other physicists proposed that maybe the information doesn't vanish, but remains somehow associated with the black hole. Perhaps it's encoded in subtle correlations in the Hawking radiation that we can't detect with current technology. Or perhaps it's stored in some quantum structure at the event horizon. These ideas were mathematically elegant but difficult to prove. Then, in the 1990s, a new development gave hope for a solution. Juan Maldacena, building on earlier work in string theory, discovered a profound correspondence between a certain type of space, with a black hole, and a quantum field theory without gravity. This adds CFT correspondence, as it's known, suggested that the information paradox might be resolvable after all. In the quantum field theory side of the correspondence, unitarity is preserved, information is not lost. This strongly suggested that the same should be true in the gravitational theory, including for black holes. But how? If information is preserved, it must somehow get out of the black hole. Yet nothing can escape from inside the event horizon. The answer, researchers began to realize, might involve quantum entanglement, the strange correlation that can exist between quantum particles even across vast distances. Perhaps the Hawking radiation is entangled with the interior of the black hole in subtle ways that allow information to leak out. In recent years, physicists have made remarkable progress on this problem. Work by Don Page and others identified something called the Page curve, which describes how the entropy, or disorder, of the Hawking radiation should evolve as the black hole evaporates. Initially, the entropy increases as more and more radiation is emitted, but then, at a certain point, it should start decreasing. This decrease represents information finally escaping the black hole, encoded in subtle correlations in the radiation. The challenge was to show that this Page curve could be derived from a consistent theory of quantum gravity. In 2019 and 2020, a series of papers by several research groups claimed to have done exactly that. They showed, using sophisticated techniques involving quantum gravity calculations, that the entropy follows the Page curve. Information is preserved after all. The key to their solution involves something called quantum extremal surfaces, or colloquially, islands. These are regions that from a certain perspective seem to be inside the black hole, but are actually accessible from outside. They represent a subtle reorganization of how we think about the interior and exterior of a black hole. The information inside the black hole isn't truly trapped. Instead, through these quantum correlations, it can be accessed from outside, encoded in the Hawking radiation. This work has been hailed as a major breakthrough. For the first time, physicists could see a clear path to resolving the information paradox. But important questions remain. These calculations were done in simplified models, mathematical toy universes that are easier to work with than our actual universe. Does the same solution apply to real black holes in our cosmos? Most physicists believe it does, but proving it rigorously is still a work in progress. Another recent development involves refining Hawking's original calculation. The original work treated gravity as a classical background, not subject to quantum effects. But when you include quantum corrections to gravity itself, something interesting happens. The Hawking radiation is no longer exactly thermal. It carries subtle quantum correlations, a kind of quantum hair that preserves information about what fell into the black hole. Researchers Xavier Calmet, Stephen Hsu, and others have shown that these quantum gravitational effects, while tiny, are crucial. they modify the Hawking radiation just enough to allow information to escape. The radiation is still mostly thermal, still dominated by random noise, but buried within it are correlations that encode the information about the black hole's contents. In principle, an infinitely patient observer with infinitely precise instruments could decode this information and reconstruct what went into the black hole. This represents a profound shift in our understanding. Black holes aren't the information destroyers we once thought. They're more like cosmic scramblers. They take information and encrypt it in extraordinarily complex ways, but they don't destroy it. The information is preserved, just hidden in patterns too subtle for us to detect with current technology. There's even been speculation about whether these quantum correlations could be detected in gravitational waves. When black holes merge, they emit ripples in space-time that we can detect with instruments like LIGO and Virgo. Perhaps these gravitational waves carry subtle signatures of the information content of the merging black holes. If we could detect these signatures, it would provide a way to test these theoretical ideas against actual observations. The black hole information paradox also connects to broader questions about the nature of space-time and reality. If information must be preserved, and if that information can somehow leak out from inside a black hole, it suggests that our usual notions of inside and outside, of what's accessible and what's not, need to be revised in quantum gravity. The event horizon might not be the absolute barrier we think it is, at least not from a quantum perspective. This has led to ideas like black hole complementarity, which suggests that the same information can appear to be in two different places, inside and outside the black hole, depending on your perspective. To someone falling into a black hole, the information crosses the event horizon and enters the interior, and nothing seems unusual. To someone remaining outside, the information is never truly lost, always accessible in principle through correlations in the Hawking radiation. Both perspectives are somehow simultaneously true, reconciled by the fact that no single observer can see both at once. These ideas push the boundaries of physics, forcing us to think about reality in new ways. They suggest that at the deepest level, space-time itself might be emergent, arising from more fundamental quantum information. The geometry of space-time, the very fabric of the universe, might be a kind of holographic projection of quantum states living on its boundary. For now, these remain theoretical investigations. We don't have quantum gravity experiments. We can't create black holes in laboratories to test these ideas. But the mathematical consistency, the way different approaches converge on similar answers, gives physicists confidence that they're on the right track. The information paradox, once thought to be an insurmountable problem threatening the foundations of physics, now seems to be pointing the way toward a deeper understanding of quantum gravity. And perhaps most remarkably, this resolution came not from abandoning our fundamental theories, but from taking them more seriously, pushing them further, exploring their implications more carefully. Quantum mechanics and general relativity, the two pillars of modern physics, can coexist after all. The universe, it seems, is more subtle than we imagined, but also more consistent. Information is preserved even by black holes, and the universe remembers in its own quantum way everything that has ever happened within it. Imagine looking at a city at night from an airplane. You see light scattered across the landscape, marking buildings, streets and neighbourhoods, but you know that what you're seeing is just a fraction of what's actually there. Most of the city, the buildings themselves, the roads, the infrastructure, remains dark and invisible in the night. You can only infer its existence from the pattern of lights and from your knowledge of how cities work. This is essentially the situation astronomers face when they look at the universe. The stars, galaxies, and gas clouds we can see all the matter that emits, absorbs, or reflects light represents only about 15% of all the matter in the cosmos. The other 85% is completely dark. It doesn't interact with light at all. We can't see it directly, but we know it's there because of its gravitational effects. This invisible stuff is called dark matter, and it's one of the deepest mysteries in modern physics. The story of dark matter begins in the 1930s with an astronomer named Fritz Zwicky studying the Coma cluster, a large group of galaxies about 320 million light-years from Earth. Zwicky was measuring how fast the galaxies in the cluster were moving. He knew that for the cluster to hold together, for its gravity to keep the galaxies from flying apart, there needed to be enough mass to provide the necessary gravitational attraction. But when he added up all the mass he could see, all the stars in all the galaxies, it wasn't nearly enough. The galaxies were moving too fast. By his calculations, the cluster needed about 400 times more mass than was visible to explain the motions he observed. He called this unseen mass dunkle Materie, German for dark matter. For decades, Zwicky's observation was largely ignored or dismissed. Perhaps his calculations were wrong. Perhaps there was simply more regular matter that we couldn't see, like dim stars or dark clouds of gas. But in the 1970s, astronomer Vera Rubin provided compelling new evidence that dark matter was real and pervasive. Rubin was studying how galaxies rotate. She measured the speeds of stars at different distances from the galactic centre. According to Newton's laws of gravity, stars farther out should move slower, just as planets farther from the Sun orbit more slowly. But that's not what Rubin found. Stars at the edges of galaxies were moving just as fast as stars closer to the centre. The rotation curves, as they're called, stayed flat instead of declining. This could only mean one thing. There must be much more mass in the galaxy than we can see, extending far beyond the visible disk of stars. This dark matter forms a halo around the galaxy, its gravity keeping the outer stars moving fast. And it wasn't just one galaxy. Rubin and others found this pattern in galaxy after galaxy. Dark matter seemed to be everywhere. Since then, evidence for dark matter has accumulated from many different sources. We see its effects in the way light bends around massive galaxy clusters, a phenomenon called gravitational lensing predicted by Einstein's general relativity. The mass of these clusters curves space-time, and light travelling through this curved space bends, creating distorted images of galaxies behind the cluster. By studying these distortions, astronomers can map the distribution of mass in the cluster, and what they find matches dark matter predictions perfectly. In 2006, observations of the Bullet cluster provided what many consider the most direct evidence for dark matter. The Bullet cluster is actually two galaxy clusters that collided and passed through each other at enormous speed. When the collision occurred, the hot gas in each cluster, which makes up most of the normal matter, slammed together and slowed down due to electromagnetic interactions. You can see this hot gas glowing in X-rays, but the dark matter in each cluster barely interacted at all. It passed right through, carrying on with only minor perturbations. When astronomers used gravitational lensing to map where the mass actually is, they found it was separated from where the visible gas is. The mass was still travelling with the galaxies, not with the gas. This separation, this difference between where most of the mass is and where most of the visible matter is exactly what you'd expect if dark matter exists and is collisionless. It's extremely hard to explain any other way. The cosmic microwave background radiation, the afterglow of the Big Bang, also provides evidence for dark matter. The tiny temperature fluctuations in this radiation, measured with exquisite precision by satellites like Planck, tell us about the conditions in the early universe. The pattern of these fluctuations depends on the amount and type of matter present. When cosmologists run simulations with different amounts of dark matter, only one scenario matches what we observe: a universe where dark matter outweighs normal matter by about 6 to 1. So the evidence is overwhelming. Dark matter exists, it's abundant, and its gravity shapes the large-scale structure of the universe. But what is it? This is where the mystery deepens. Despite decades of searching, we still don't know what dark matter is made of. The leading candidate for many years has been something called WIMPs, weakly interacting massive particles. These would be new particles, not part of the standard model of particle physics, that interact only through gravity and possibly the weak nuclear force. They would be their own antiparticles, meaning when two WIMPs collide they annihilate each other. the energy and abundance of these particles could naturally explain the amount of dark matter we observe. Physicists have built incredibly sensitive detectors to search for WIMPs, placing them deep underground to shield them from cosmic rays and other interference. These detectors are looking for the incredibly rare event where a WIMP passes through Earth and collides with an atomic nucleus in the detector. The collision would release a tiny amount of energy, perhaps heating the detector by a fraction of a degree or creating a flash of light. Experiments like LUX and its successor LZ, located in a former gold mine in South Dakota, have searched for these interactions with exquisite sensitivity. They've pushed the limits on how strongly WIMPs can interact with normal matter to levels that are starting to challenge the original theoretical predictions, and they've found nothing. At least, nothing that can definitively be attributed to WIMPs. The detectors are working perfectly, but the WIMPs, if they exist, are refusing to show up. This doesn't mean WIMPs don't exist. It might just mean they interact even more weakly than we thought, making them even harder to detect. Or perhaps they only interact at specific energies we haven't tested yet. But it does mean that other candidates are getting more attention. One alternative is the axion, a hypothetical particle originally proposed to solve a different problem in particle physics. Axions would be extremely light, much lighter than any known particle, and they would interact incredibly weakly with normal matter. But there could be so many of them that collectively they make up the dark matter. Experiments using powerful magnetic fields are searching for the subtle signals that axions might produce. Another possibility is that dark matter isn't made of particles at all. Perhaps it's primordial black holes, formed in the very early universe from density fluctuations shortly after the Big Bang. These wouldn't be the stellar mass black holes formed from dying stars, but much smaller objects, perhaps ranging from the mass of an asteroid to a few times the mass of the Sun. They would be invisible, as black holes are, but their gravity would be detectable. Astronomers search for these primordial black holes using gravitational microlensing. When a massive object passes in front of a background star, its gravity acts as a lens, briefly brightening the star's light. By monitoring millions of stars, astronomers can detect these brief brightenings and infer the presence of dark objects. So far, this method has found some candidates, but not enough to account for all the dark matter. Yet another intriguing possibility is that dark matter might not exist at all. Perhaps what we're seeing isn't evidence for unseen matter, but rather evidence that our theory of gravity, general relativity, breaks down on large scales. Theories like MOND, modified Newtonian dynamics, propose that gravity behaves differently when accelerations are extremely small, as they are in the outer regions of galaxies. This modified gravity could explain galaxy rotation curves without requiring dark matter. But MOND and similar theories struggle to explain other observations, particularly the bullet cluster and the cosmic microwave background. Most physicists remain convinced that dark matter is real, and that it's made of particles we haven't discovered yet. The search continues, with new experiments coming online and new detection techniques being developed. In recent years, researchers have also realized that dark matter might be hiding in plain sight in other ways. When the Large Hadron Collider smashes protons together at enormous energies, it might be creating dark matter particles. These particles would immediately escape the detectors, carrying away energy and momentum. By carefully accounting for all the visible particles produced in a collision and noticing when energy is missing, physicists might infer dark matter creation. The cosmological implications of dark matter are profound. In the early universe, dark matter began clumping together under its own gravity, before normal matter could. Because dark matter doesn't interact with radiation, it could collapse freely, while normal matter was held back by radiation pressure. These dark matter clumps created the gravitational wells into which normal matter later fell, forming the first stars and galaxies. Computer simulations of cosmic structure formation, running with and without dark matter, show striking differences. Without dark matter, galaxies form later and have very different properties than what we observe. With dark matter, the simulations produce a universe that looks remarkably like our own, with the same large-scale structure, the same patterns of galaxy clusters and voids, the same timing for when different structures formed. This large-scale structure, sometimes called the cosmic web, is one of the most beautiful patterns in nature. Filaments of galaxies stretch across hundreds of millions of light-years, connected by nodes where massive galaxy clusters reside, separated by vast voids with almost nothing in them. This web is the scaffolding upon which the visible universe is built, and it's shaped primarily by dark matter. Yet for all our knowledge about what dark matter does, its true nature remains elusive. Every year brings new experiments, new observations, new theoretical ideas. Perhaps dark matter is a complex sector unto itself, with many different types of dark particles forming a hidden world invisible to us. Perhaps it's something simpler, a single type of particle that we just haven't detected yet. Or perhaps the solution will require an entirely new framework, a deeper understanding of physics that connects dark matter to other mysteries like dark energy. The search for dark matter is more than just an attempt to identify an unknown particle. It's a quest to understand the fundamental composition of the universe, to know what most of the cosmos is actually made of. And in that search, in the careful experiments and the meticulous observations, we're pushing the boundaries of human knowledge, exploring the darkness to find what's hidden there. We've journeyed tonight through some of the most perplexing mysteries that grace our sky. From fast radio bursts that flash for milliseconds, yet release the energy of suns, to interstellar visitors whose behaviour defies our expectations, to radio signals that might have carried messages from across the cosmos, to black holes that somehow preserve information despite consuming everything that falls into them, to the invisible dark matter that makes up most of the universe's mass. Each mystery reveals something profound about the nature of reality. What strikes me most about these cosmic enigmas is not just their strangeness, but what they tell us about the scientific process itself. Science doesn't always proceed by building on certainties. Sometimes it advances by embracing mysteries, by admitting when we don't understand something, and by having the humility to keep searching for answers even when those answers prove elusive. The fast radio bursts we detect today might eventually be as well understood as pulsars are now, phenomena that once seemed inexplicable, but became tools for precise physics. Oumuamua might be the first of many interstellar visitors that teach us about the diversity of planetary systems across the galaxy. The wow signal might find its explanation in astrophysical processes we're only beginning to comprehend. The information paradox might lead us to a deeper theory of quantum gravity that unifies our understanding of the very large and the very small. And dark matter might reveal itself as a new fundamental particle, opening an entirely new chapter in physics. Or perhaps some of these mysteries will remain unsolved for generations. Perhaps future astronomers will still debate the origin of the wow signal. Perhaps dark matter will continue to elude direct detection. But even in the persistence of mystery, there's value. These unknowns drive us forward. They inspire new questions, new experiments, new ways of thinking about the universe. The cosmos is not a solved puzzle. It's a living mystery, constantly revealing new aspects of itself while hiding others. Every answer we find raises new questions. Every solved problem opens new avenues of inquiry. And in that endless exploration, in that perpetual dance between the known and the unknown, we find one of the deepest satisfactions that science can offer. So the next time you look up at the night sky, remember that you're not just seeing points of light, you're seeing mysteries, each star and galaxy harbouring secrets we're still unravelling. You're seeing cosmic laboratories where the laws of physics are tested under the most extreme conditions. You're seeing a universe that's stranger and more wonderful than we ever imagined. The most mysterious objects in our sky aren't just out there in space. They're invitations to wonder, to question, to seek understanding. They remind us that despite all we've learned, despite the vast edifice of knowledge we've built, the universe still has the power to surprise us, to show us phenomena we never predicted, to reveal depths we never suspected. And perhaps that's exactly how it should be. A universe we fully understood would be a universe without wonder. But ours is a universe filled with mysteries, each one a reminder that there's always more to discover, always more to learn, always another horizon to explore. If you enjoyed this journey through the cosmic unknown, please consider liking this video and subscribing to the channel. Hit that notification bell so you won't miss our next exploration of the fascinating science that surrounds us. Share your thoughts in the comments. What mysteries of the universe captivate you most? What would you like us to explore next? Until next time, keep looking up, keep wondering, keep questioning. Because in those questions lie the seeds of tomorrow's discoveries. The universe is waiting to reveal its secrets, and who knows? Perhaps the next great mystery, the next paradigm-shifting observation, is just waiting for someone to notice it. Perhaps that someone could be you. Thank you for joining me on this voyage through the mysterious sky above. Sweet dreams and clear skies.